Hello students, and welcome to section 2.7b, solving equations and inequalities algebraically and graphically. To start with, this is a warm-up, as you can tell, of which I do want you to try out on your own. Just to highlight, we're going to be taking a look at obviously inequalities of a whole variety of kind of nature here, of which you can see you've got a linear inequality, wherein if you get it set to 0, you're going to notice that because it's less than, for example, 0, you're going to note it's negative output values you're striving for, and also open values at the critical points that you decipher. Make sure that every one of these problems you set to 0. This problem is an exception, of course. Although it's not an inequality, you're going to treat it in a very similar manner. You'll set it equal to 0, and then you'll find a critical value and justify, for all of these really, which interval is going to dictate the final answer, or will be dictated based upon what the inequality is. So you'll pick a test value, like for example left of +4 and right of +4, and see which interval works, or intervals for that matter. So please try that warm-up. It's a nice precursor to today's discussion, which more specifically digs into solving rational equations, but also inequalities. We have already done problems of which you do make a number line and you find critical values and then decipher test intervals, and then from there figure out your final answer once you denote which intervals work based on the inequality. For this first problem, however, it's not going to entail the exact same amount of work that you saw in the warm-up, but we are going to take a look at problems pretty much in this particular section where you'll deal with rational functions, but eventually your equation will turn into an inequality or equal sign. So for this problem, to solve this rational equation, you'll need to find a common denominator, and I strongly urge that you find a common denominator right away. As it turns out, x squared minus 2x is factorable as x times the quantity x minus 2, and because these other two denominators have both parts, you're going to utilize, again, this as the LCD, but you're going to multiply this second fraction, as you can see here, by x minus 2 over x minus 2. And this third fraction by x over x. Every single denominator, when you do this, it's quite nice, as you can see, every single denominator is going to cancel. So what you'll then end up having is 10 plus 4 distributed x minus 8 equals 5x. Keep in mind we're trying to solve for x here, so you'll subtract 4x to get x, and then 10 minus 8, which ends up being 2. Turns out that x equals 2 is not a solution because back at the very beginning you should remind yourself that there are two values that you cannot have for x, so that you're dividing by 0 in effect, which is not defined. So 0, if you recall, if you plug in 0 here, it's actually going to be undefined, but also if you plug in 2 here, it's going to be undefined. So look at your denominator and make those determinations as soon as you can. I didn't discuss it from the beginning because I wanted you to see the process. You do have to do this at the beginning or the end to make sure that your answer is in fact a solution, which in this case, of course, it's not. Because we can't count x equals 2, thanks to this particular derivation, we have no solution to the problem. If you were to graph this left side of the equation as y1 and this right side as y2, the two rational functions do not intersect. The boundary algorithm. Now you may recall we've already touched upon the boundary algorithm, wherein we did use, as we discussed, test intervals. Plotting test points may help. Picking a test point per interval and test intervals, and then including intervals that make the inequality true. I encourage you to take a look at these two examples to start with on your own. These two examples nicely convey the same ideas that we've discussed in the past with polynomial inequalities when we spent time back a few sections ago. Turns out that you can set up, for this first problem at least, two different kind of inequalities, of which I've combined with this AND compound inequality. And in a similar manner, although it's an OR statement, you'll have two inequalities as well in the other problem. Notice my number line. my interval that does work versus my intervals that do not, for number 1, but also for number 2. Similar problem, but of course the inequality is different. So please take a look at both of those. Please try those on your own, noting all the nuances that we've seen in the past. We do want to go ahead and take a look, though, together at the rational inequality. So the segue from the last couple problems, as well as the warm-up from today, including the problem we just solved with rational expressions in the rational equation format, we're going to assess how we're going to go about using the boundary algorithm. Remember the following: include undefined values as a boundary point, which is any value that would cause the denominator to be equal to 0, but also go through those same exact steps in terms of determining test intervals and picking a test point per interval. So let's go ahead and take a look. To kickstart the problem, you can already see here that it's set to what we want it to be set to, which is greater than or equal to 0. You may see problems where, for example, 3 possibly is starting off on the right side of the inequality. I urge you always to move whatever you can over to whatever side such that it's, in this case, greater than or equal to 0. Or in other cases, of course, less than, greater than, that kind of thing. But this is already set up exactly how we want. So first and foremost, we want positive outputs because greater than or equal to implies positive, and because it's greater than or equal to, we want closed points at the intervals, or excuse me, at the critical numbers, so that we can decipher our intervals appropriately from there. So the process that I went about here, if you recall from polynomial inequalities, we changed the problem to an equal sign. So this actually looks more like the problem we did with no solution a moment ago. I got a common denominator here of x plus 2, which you can hopefully see now that I've multiplied minus 3 by x plus 2 over x plus 2. We'll be able to then subtract the numerators. So there you have it in my next step: x plus 12 minus 3x minus 6 all over x plus 2. And that still equals 0. The numerator you can simplify as such: negative 2x plus 6, and that's still over x plus 2, still equals 0. And then you have a GCF here, as you can see, what appears to be negative 2, which leads you to this factored form, to negative 2 quantity x minus 3 all over x plus 2. One critical thing that you don't want to fall into the trap of is multiplying both sides by x plus 2 and lose that factor, or lose that entire quantity. So as it turns out, leave your answer in this particular format, because in the numerator you're going to be able to set it equal to 0, noting that x equals 3 will be a critical value on the number line that you create, which is closed. Again, noting it's closed thanks to the original inequality. Okay, and the other critical value is where the graph would have a vertical asymptote. In other words, where it's undefined, right? Undefined values we already know to be vertical asymptotes in the context of the graph, which I would argue you should also do. If you want to get a better picture of this, you can see that the graph of this function will have a vertical asymptote at negative 2. And as it turns out, it'll have an x-intercept, not surprisingly, hopefully recall from last section, an x-intercept at 3. It is undefined, like I said, at negative 2, so it's an open circle. So then you'll test values left of negative 2 or less than negative 2, which don't technically work. You'll test numbers between negative 2 and 3, which do work. Any number between those two values should work. And then any number to the right of 3 or greater than 3 will not work. When I say test values, you're literally going to plug in, let's say, negative 3, for example, for x here and here. And if you do the math, it will not be greater than or equal to 0. If you plug a number, let's say in between, a number like 0 is always pretty nice to substitute in. If you plug in 0 here and here, for example, that's nice. That's simply 12 halves, or 6. 6 minus 3, of course, is 3, which is positive. Because it's positive, we do want a shade or graph in between. And then any number bigger than 3, of course, will not work. And you can test that theory. It will end up being negative, just as, for example, if you plug in a negative 3 or negative 4 and so on, you'll get an output of a negative value, which again, we don't want. We want positive values. So again, you're using the same analysis. You can use your store feature on your calculator. You can graph it, like I said, to make your analysis. What I do want to do, though, is go ahead and note your final answer, of course. There it is. What I do want to note is how you can continue this idea of solving rational inequalities, but using this little worksheet that we've stumbled upon to help you guys kind of go through the process. Because there's going to be a variety of problems that you're going to encounter, very much like what we've seen on the very last problem there. Objectives. First, solve rational inequalities algebraically. They say use a sign chart. We've seen sign charts in the past. I haven't used them a ton because, frankly, you can use your number line and make the assessment by plugging in numbers as we've seen in the past, left and right of your critical values. Solve rational inequalities using a base graph. In order to solve rational inequalities, it is necessary to find both the zeros and where the inequality is undefined, as I've already described. So for this first example, it says solve 6 over x plus 2 greater than or equal to 0. So right off the bat, it's great that it's set greater than or equal to 0. If it isn't, you need to do some extra steps at the beginning just to get it to be greater than or equal to 0, for example. Because it's greater than or equal to 0, it's positive, and because it's an or equal to, essentially, again, it's closed. I got a common denominator here of x, so I multiplied a numerator and denominator of that term by x over x, multiplied the whole thing, of course, by x over x, in other words, and I'm left then with this quantity. The numerator, if you set it equal to 0, there's one critical value. The denominator, if you set it equal to 0, there's another critical value. Now notice I set it not equal to 0 because technically, again, if you recall, we should envision here a vertical asymptote at 0. X equals -3 is an x-intercept of this rational function. It turns out left of -3 works, as all of this notation describes. Well, it says, including the language, the 0 from the numerator, x is equal to -3, and the inequality is undefined at x equals 0. As we again described back on the last problem, this is a vertical asymptote that we're identifying with. These are called critical numbers or critical values, same thing. Place the critical numbers of -3 and 0 on the number line. It does also kind of go into arbitrarily choosing values in each interval, which I still recommend you do. Maybe not just for 6 plus 2x to get 2 negatives and x to get looks to be 2 negatives, both of which end up being multiplied together yielding, or dividing yielding a positive output. That is a solution technically, as we already discussed back here. In the middle here, in between -3 and 0, you'll get negative values because these two divided by those two end up being negative. And then lastly, it does work if you divide positive positive over positive positive. Okay, I don't particularly use the sign chart on my analyses when I've done it with you in the past, so I am going to take a moment here and show you what the graph actually looks like. So why don't we do that here? So the graph of our function, simply if you type in 6 over x plus 2, I'm also going to maybe note here, why not, y equals 0. So you're graphing the left side as y1 and the right side is y2. And if we go through the process, so let's take a look in the process. If we go ahead and simply hit zoom 6, we'll go ahead and see here that the graph in fact has an x-intercept at -3 as we expected it would. It also has a vertical asymptote at x equals 0 as we also expected that it should. It also happens to have a horizontal asymptote as well, which you could probably quickly and easily see here based on the way we've written this. 2 over 1, thanks to the leading coefficient here of 2 and leading coefficient of there of 1, dividing them because the degree in the numerator is 1 equal to the degree in the denominator of 1. So y equals 2 is your horizontal asymptote. Again, because we're trying to solve the inequality to start with that looked like this, we want values that are positive. So if you can already see here, to the left of -3, all of your y's are above the x-axis, left of -3. That's a nice quick way to decipher this. If you did use your graphing calculator store feature, you can plug in -4 and you'll find that plugging in -4 will yield for example, because it's left of -3, yield positive outputs. Similarly, anything between -3 and 0 will have negative outputs, so it won't work. Whether you use the graph or the store feature, you'll see that. And then everything to the right of 0 will have positive outputs. Okay, and that's very clear, of course, in looking at simply just the graph. The answer overall, as you can see, and I've changed this symbol to, instead of an and notationally, I use the symbol of this union. So -infinity to -3 in union with 0 to infinity.